So first I want to begin by thanking the organizers for bringing all of us together for this wonderful conference. I've learned a ton in every lecture. And I also especially want to thank David for including rigidity theory in his list of topics and for asking me to speak about it. So my talk is sort of in two halves. The first half, I'm going to pick up where David left off with combinatorial rigidity theory. And then in the second half of the talk, I want to talk about what you can say when the combinatorics fail, sort of when you have the failure of genericity and what kinds of polynomial methods we might use in those cases to understand what's going on. So I want to begin by talking about bar and joint rigidity in 3D. Okay, so we have this beautiful theorem of Lemon, Polachek, Geringer in the plane, giving us a complete combinatorial characterization of minimal generic infinitesimal rigidity in the plane. And so the natural question to ask is, well, does this generalize to 3 space? And this is like where sort of the big money is, because you can imagine proteins folding and all sorts of things in 3 space where you want to know, are they rigid or flexible? Okay, so let's think about what we might expect. So you might say, well, is it true that if you have a generic framework associated to a graph, is minimally infinitesimally rigid in R3, if and only if, so what should the generalization look like? Well, each vertex is like a point in R3, and so each vertex has 3 degrees of freedom since it's in 3 space. Okay, so we might say, okay, you have 3 v degrees of freedom in this system that you want to eliminate. How many of them can you eliminate? Well, by placing bars between joints, I can only eliminate relative motion between. I can't eliminate the possibility of me picking up my entire framework, moving it around, rotating, etc. So in 3 space, there's a 6, the special Euclidean group has dimension 6. So at best, by adding bars to this system of joints, I can hope to remove 3v minus 6 degrees of freedom. Okay? And what you would hope is, just like in the plane, if you put those bars in sort of sparsely enough so that you're not ever putting a bar in where it would be redundant, then you'd hope that a theorem like this would hold. So if I take any subset of the vertices and I look at the induced graph on that subset, the number of edges in the induced graph is 3 times the number of vertices minus 6, less than or equal to that. So you'd hope that this would work, but it fails. And so here's the famous or infamous example showing the failure of these kind of counting conditions for 3D rigidity. So what is this picture? It's a little funny looking. It's called the double banana. So one banana it's 2 tetrahedra glued together on a facet, right? So that's one banana. And then I have another banana just like it, and then I attach them at these vertices. A tetrahedron is rigid. 2 tetrahedra glued together on a face, that's rigid. So I have 2 rigid bananas, but the thing goes like this, right? So the thing has a motion, and it's satisfied. If you're bored, you can check it satisfies these counting conditions. Okay, so you might say, okay, then the first half of her talk is really short. Is that the end of combinatorial rigidity theory? And so what I want to do now, though, is turn and talk about some other flavors of combinatorial rigidity theory where there have been great successes. And the first one is one that David already talked about briefly in his lecture. This is body and bar rigidity theory. So I'm thinking really about what other kinds of frameworks arise from constraint systems. So what is a body-bar framework? It's in RD, and so I'm going to actually embed RD into projective D space. So I'm going to have n full-dimensional rigid bodies in RD embedded in PD, connected at flexible joints by fixed length bars. Okay, so I actually have such a framework here. This is a real life realization using plates stolen from our reception on the first day. And so you can see that what I've done, I bought pins and straws at Kroger. And so the pins are the flexible joints, and this is, it's not rigid. It's not rigid with only 2, but if I generically place this last straw in, Oh, well, really, oh, that looks, hold on, really generically. Let's do that. This looks pretty rigid, okay? Up to, you know, I've got pins and bars, and it's not a perfect realization of this by any means. Okay? And so the question we ask is the same question: is a given framework of bodies and bars rigid or flexible? So what do we do in the combinatorial theory? Given such a framework, what kind of mathematical object do we associate to it? Well, so instead of a graph, as David said, we're going to associate a multigraph to it. So there's going to be one vertex for each rigid body and one bar, or one edge for each bar. And there's a beautiful theorem due first to Tay and then to White and Whiteley, that a generic framework associated to a multigraph is minimally infinitesimally rigid in PD if and only if. So here K is the dimension of the special Euclidean group, so that D plus 1 choose 2 that we've seen before. So the number of edges in the graph is K times V minus K. And then we have that same sparsity condition that we've seen already today in the Lemon-Polachek-Geringer theorem, that if I take any subset of the vertices and I look at the induced graph on that subset, then the number of edges in that induced graph is less than or equal to K times the vertices minus K. Right? So I want to actually indicate a little bit of how the proof goes for this for you. And to do that, I'll need to restate this theorem. And so it turns out, due to theorems of Nash, Williams, and Tutt, that counting condition can be restated in terms of trees. So it's equivalent to saying that the multigraph G can be decomposed as a union of K edge disjoint spanning trees. Okay? And so you can see up here it's trivial. Here, K, I'm in the plane, so this is a planar bar and body framework. So D plus 1 choose 2 is 3, so K is 3. Can I decompose that as 3 edge disjoint spanning trees? Yeah, one edge is one spanning tree, another edge is another spanning tree, and the third edge is the third spanning tree. All right, so that's trivial in that example. I just briefly, before I go to the proof, I want to give an aside saying that you can actually restate the Lemon-Polachek-Geringer theorem in this kind of a language due to a result of Ruth Haas, who said that it's equivalent to, if I can add any edge to G, and I might have to create a multigraph, allow myself to create a multigraph when I do that, I end up with a graph that can be decomposed into 2 edge disjoint spanning trees. So you can see, like, if I start with the triangle, which is minimally infinitesimally rigid in the plane, if I add any edge, I'd have to double one of the triangle edges, so I'll have to get a multigraph. But if I double one of those edges, then I can go like one spanning tree, another spanning tree, right? And if I have more choices over here, I could add the diagonal and then get 2 spanning trees, or I could double an edge and then get 2 spanning trees. All right, so it really does parallel the 2-dimensional theory. So the presentation of this result that I want to give is from this paper of White and Whiteley, The Algebraic Geometry of Motions of Bar and Body Frameworks from 1987. It's a wonderful paper. It's beautiful. I reread it and read it and reread it and reread it, and every time I reread it, I find something I think, wow, that's in there too. I think it's something that the community of people who are interested in frameworks, the algebra in it, there's Grassmanians and homogeneous coordinate rings and Fluker coordinates. It was stuff where they were like, this is a little foreign to us. And so I think it's the kind of thing where the methods are beautiful, but the community that was involved interested in the questions wasn't quite so interested in the methods. And I think they've been really reaching out to algebraists. I think they're thrilled that we're doing this here, because they definitely want people who know the algebraic theory to get involved in rigidity theory. I think there are still a lot of opportunities for people with the algebraic background to prove some interesting stuff. So I want to tell you about this paper and this theorem. So the sort of way that combinatorial rigidity theory goes is we're going to end up prove things that hold only generically. So the combinatorics can't tell us about sort of special configurations that might occur. We're going to linearize the problem and work infinitesimally always, and we're going to work with a rigidity matrix. Okay. So we're going to form a rigidity matrix here, as David did in his morning lecture. And it will have, again, one row for each bar. So if there are m bars, it'll have m rows. And it's going to have k vertices for each, or k columns for each vertex. So it's an m by kn rigidity matrix, where again, k is the dimension of the group of the special Euclidean motions. So what's going to go in these rows? So what David showed us in the morning in his rows are really sort of the vectors that point from one vertex to another. So xi minus xj. And there we were really saying that you're saying that the vector that points along the bar has to be orthogonal to the relative velocities. So your initial velocities aren't like pulling or pushing compressing the bars. Here, I'm not going to go through the derivation. It's not that hard. It just takes us through these screw motions in R3, and I don't want to go through all of that. But it's beautiful. But what sort of will make sense to us, because we have algebraic background, most of us, is that the thing that's going to take the place of xi minus xj, in this case, are going to be the Plücker coordinates of the line that goes along the bar, joining vertex I to vertex j. So here my xij's in this part of the talk are going to be Plücker coordinates. Okay? And so I want to study the generic minimally rigid case. So again, I'm going to restrict to where the number of bars is kn minus k. And so my rigidity matrix is going to look like this. So that's a sort of typical row in my rigidity matrix. It's the ith row, and I'm showing you the jth, the sort of columns associated to the jth vertex. So that xij is k columns wide. Okay, so it's xij and minus xij. And I told you I can't eliminate the trivial motions of my framework by just adding bars. But what you might be said, well, you can eliminate the trivial motions algebraically. Here's what you can do. Just think about tying down, so holding fast one of these bodies, and you can tie it down by eliminating the motions of this body. And the way you do that algebraically is you add k rows to the rigidity matrix, and you put a k by k identity matrix in the columns corresponding to the body you're tying down. Okay, so that'll stop the motions. And that has the added benefit of giving us a square matrix, and now we can take its determinant. And they called the determinant of this matrix the pure condition associated to the graph. And so it's a polynomial in all these xij's. So I want to sort of show you the key idea, at least of one half of this, if and only if proof in an example. So this is an example that actually appears in their paper. This is a 3-frame in P2. You can check it has how many it has. So we should have 3 times 3 minus 3 edges if it's minimally rigid, and it has 9 minus 3 is 6 edges. I've labeled each edge by a 3 vector, which corresponds to the Plücker coordinates of the line a line along the bar that would go from like vertex 1 to vertex 2, or something like that. Okay? And so this is what the rigidity matrix would look like. I have in the first row, corresponding to one of the 2 bars joining vertex 1 to vertex 2, I'd have A1, A2, A3 in the columns associated to body 1, minus A1, minus A2, minus A3 in the columns associated to body 2, and zeros in the columns associated to body 3, because they're not involved. That's not involved in that bar. I have 2 bars between vertices 1 and 2, so I have 2 rows that kind of look with that pattern. And then I move on to the bars between 1 and 3. I have 2 of those. I have the bars between 2 and 3, 2 of those. And then I'm tying down body 1 with that 3 by 3 identity matrix. Okay. So how am I going to somehow show that the determinant of this being non-zero is equivalent to having 3 edge disjoint spanning trees? Well, here's their idea. Rearrange the columns. Okay. So what I'm going to do is I'm going to take the first column associated to each of my bodies and push all of those to the beginning. So I'll get sort of n columns. Here n is 3 because I have 3 vertices, but I couldn't draw a bigger matrix, so that's what we're stuck with. So 3 plays 2 roles, unfortunately, here. So I put all my first columns, then I put all my second columns, then I put all my third columns. And then you look at this and you say, oh, hey, so you have essentially like k copies of the same matrix, just with different indices. And then if you're really like into graph theory and matrices, you go, hey, isn't that like essentially the incidence matrix? Maybe it's transposed, maybe I've multiplied each row by a non-zero scalar, but essentially these are incidence matrices for these underlying graphs. Okay? And so then the trick is to say, okay, now I'm going to expand this determinant by n minors. So I'm going to go into my first n columns and pick 3 of them. And if I want to get a non-zero determinant there, I'm going to have to pick 2 of these rows that correspond to a tree, and the 1, 0, 0 row in the bottom. That's the only way this is going to work. Okay. So if the determinant is non-zero, one of these products that I get by doing n by n minor, n by n minor, n by n minor has to be non-zero. And those n by n minors, each of them is going to correspond to a tree. And if you think about the rules for expanding determinants, I can't have used any of the sort of edges more than once, so it really will be a decomposition of this multigraph into 3 edge disjoint spanning trees. Okay. So that's how the proof goes. Yeah.
Is there any way to use, there's this, I can't remember the exact formulation, but there's some matrix tree theorem that says number of spanning trees in the graph are related to some kind of determinant thing. Somebody who's more combinatorial than you might remember this.
Maybe. I don't know.
Is there some? There's some, anyhow.
Very possibly. Very possibly, yeah. So here it is. Here's one of these non-zero choices. So I have my red spanning tree, my green spanning tree, and my blue spanning tree. And you can see that if I did the red minor times the blue minor times the green minor, I'd get something that's non-zero. Okay. All right. So that's the key idea of the proof, is to rearrange the column, expand via trees. And then the other direction is if you have a decomposition in terms of trees, you can use that in a clever way to kind of specialize and show that the polynomial is non-zero someplace. And if it's non-zero at a point, it's a non-zero polynomial. So you're kind of done. Okay. So that's the proof of the White and Whiteley theorem. I think it's really lovely. And so I want to show you another flavor of combinatorial rigidity theory. And this is body Cad Frameworks. They were introduced by Audrey St. John in her thesis. And in this paper by Haller, Kirk Haller was at SolidWorks. And so I think these graphs were created in SolidWorks. Or these figures were created in SolidWorks. And so Mira Setharam, Audrey St. John, Neil White, I think that's the whole group that's involved in that paper. So these are, so body bar frameworks were, you had these rigid bodies and you specified point-point distance constraints between them. That's what bars are. They're just, you're saying, I'm constraining the distance between points in my bodies. Well, points are just affine linear spaces. So maybe what we could do is allow ourselves to put other kinds of affine linear spaces on our rigid bodies and put other kinds of geometric constraints between those affine linear spaces. So for example, in figure 1, what we've got is a cube and a tetrahedron. I've affixed a line to each of them, and I'm saying those 2 lines have to coincide. So what can happen then? If I hold the cube fixed, the tetrahedron can slide up and down, it can rotate like this, but I've eliminated a lot of different kinds of motions. I can't pull it this way, I can't rotate it that way anymore, etc. Okay? Here I have other kinds of constraints that we're allowing line, plane, angle constraints, point, plane, distance constraints. It's sort of very clever here, the CAD in there. So these are constraints that arise in computer-aided design software packages. But the CAD in this also comes from coincidence, angular, and distance constraints. So there are two meanings of CAD. I didn't come up with that. Two meanings of CAD in this body CAD world.
So these are different than like the joints you see in kinematics.
Yeah.
Like sliding.
Yeah.
Image and stuff.
Yeah.
And so they contain that, but they seem more general.
Yeah, and so the motivation for this, right, is that all kinds of people use CAD software. And so like if you're an engineer and you're trying to build something and you're putting constraints in among these parts, you at some point, like, it just says like over constrained, like you've put in too many constraints. And the idea is that if you had a nice combinatorial theory where you could maybe say, okay, given that system, I can find you some minimally rigid subsystems. So like if you took out this constraint, it would be consistent again, et cetera, et cetera. So that's the motivation for this research, is to give better user feedback in CAD software. And so we're asking the question, does a given set of constraints specify an infinitesimally rigid structure? So what's different here? The constraints, as we saw, may restrict more than one degree of freedom. And some constraints are only going to restrict rotational degrees of freedom. And it turns out that I can't eliminate all the internal degrees of freedom of a framework like this just by specifying angle constraints. So those have to be treated in a kind of special way in the matrix. So here, this is an example, actually, of a minimally rigid framework. Just to go through how this works, the blue dashed line is a line-line coincidence. Okay, and that turns out that that will eliminate 4 degrees of freedom. And so I can still like slide up and down this way and rotate this way. Those are sort of my 2 degrees of freedom left. I then have a point-plane coincidence. So there's a red plane affixed to the top of the cube, and a red point on that hexagonal prism. And I'm saying that that point has to lie in that plane. So it's like an infinite plane, right? And that will stop my motion, my sliding motion up and down, right? I still have the rotational motion, and I stop that by putting a green point on each of the rigid bodies and specifying a distance between the green points, and now I can't rotate anymore, okay? So of course, there are generic and non-generic. This is sufficiently generic. I could have, if I did that last constraint in a non-generic way, I wouldn't have stopped all my motions. Can anyone see a way of doing it non-generically where you still have a motion left?
The 2 quarters are meeting.
Where the 2 quarters? Yeah. So if I put one of the dots like sort of on that line, then it can still rotate around the line. Okay. So I have to make sure my constraints are somehow generic enough. Okay, so what combinatorial object do we associate with something like this? They called it a primitive CAD graph. So here it's a graph that has 1 vertex per body and 1 edge for each row in the rigidity matrix. So that first line-line coincidence is getting 4 rows. 2 of them are special, and they're dashed in red. They're sort of saying those correspond to just angular constraints. So we're keeping track of things that just constrain angles. And then I have my point-plane coincidence and my point-point distance. So we're going to have, again, 1 vertex per body, 1 edge per each row in the rigidity matrix, and we're partitioning the edges into angular and non-angular constraints. So what does the combinatorial characterization look like in this setting? So now we have these multigraphs with my vertex set, and my edge set has red edges and blue edges. So the red are going to correspond to the angular ones, and the blue are sort of general. And I'm going to call something an AB graph. If I can take a subset of the black edges and put them in with the red edges, and those together, I get a disjoint union of A spanning trees, and then the leftover black edges give me a disjoint union of B spanning trees, okay? And so together, then, I have a disjoint union of A plus B spanning trees, just like in the body bar case. And so the theorem is that a body in Cad framework is generically minimally infinitesimally rigid if and only if it's a 1-2 graph in 2D or a 3-3 graph in 3D where we had to omit one kind of constraint, a point-point coincidence constraint, because there's always some non-genericity in the rows of the rigidity matrix for point-point coincidences. Okay, so here we have a 1-2 frame and a 3-3 frame. All right. So what's next? Okay, so that brings me to the close of the first part of my talk. So that's combinatorial rigidity theory. There are lots of other flavors: slider, pin, panel, hinge, kinds of rigidity theories, and combinatorial successes in different circumstances. But now I want to talk about when the combinatorics fails to explain what's going on. So non-generic frameworks. And these different people call them very different names. White and Whiteley called them special frameworks in special position. Geis and Schreier called them exceptional. Some people refer to them as singular configurations. So first of all, I want to give a strong plug for why we should consider these non-generic frameworks. Okay? Because if you think about it, like that pure condition, so that's a polynomial, the non-generic frameworks are exactly the ones that are on the variety associated to that pure condition, which has measure 0 in the space of all frameworks. So if you're like into witness sets and you pick a random realization of your framework, it's going to be generic. So like with probability 1, if you ever pick a random realization of these frameworks, you're going to pick a non-generic one. So if you're like thinking probabilistically, you'd say, why should we be talking about this set of measure 0? It's like we're never going to land on it. But also, like, I think back to David's very first lecture, I think, where he wrote down that polynomial for the Lagrange multipliers problem, and Frank said, oh my gosh, it factored so well, surely you must have fine-tuned it. And David said, no, I actually just wrote it down, right? So somehow, even the random sort of generic things that humans tend to write down tend to be not so generic. And especially the things that engineers design to be useful, I claim, right? So like if you have something that has like the combinatorics of a table, you won't like have a random realization of it where like all the legs have different ways, right? So the things that are designed to be useful have a lot of symmetries that a random realization of that same object with an object with the same combinatorics wouldn't have. So I claim we actually are in that non-generic setting a lot of the time, even though probabilistically we'd never hit it. So I think that it is something we need to care about if you're thinking about things that are designed. So it really depends on your application, whether the generic setting is good enough for you or not.
Well, there's another reason. Von Pergusti makes this point that people actually want to know about mechanisms that have a motion to exploit that, and he has applications of this in his work.
Yeah.
So yeah.
And so I think also just to sort of get a really complete understanding of mechanisms of these frameworks, we want to know which ones move and why. And so I want to, this is another beautiful paper. I love this paper of Geis and Schreier. And so it's called A Family of Exceptional Stewart-Go Mechanisms of Genus 7. And so they find these realizations of the Stewart-Go platform that we saw already in David's talk. These are platforms where the bars don't have the prismatic joints, right? So they're fixed length bars, and they're moving, and we've seen pictures like this many times. These were found in a really kind of ingenious way. They used actually finite fields. So they had some kind of like they used like brute force methods over fields with very, very few elements. And then they found a way to take some of those and make them over the embeddings over the rationals. And then of course, because it's Frankel F. Schreier was involved, right? They took these curves, they plugged them into Macaulay 2, they found the graded Benny numbers, and they found that these were beautiful. They're curves of degree 12 and genus 7, and they're canonical embedding, right? So there's some surprising algebraic geometry that came out of this. And this paper is something that, you know, if the rigidity theory community didn't like the algebra in the Whiteley stuff, this is really stuff that people haven't touched. And they have a long, long list of open problems in this paper. And I think it's wide open territory for people who are, maybe you like characteristic zero, maybe you like finite fields, and you like applications. So I would definitely look this up. I think it's really, really cool. And very
Schreier finds exceptional objects this way. That's sort of is a big part of his research for many years. To turn it something more practical.
Yeah, it's really great, and yeah, highly encourage it. So let's think about non-generic frameworks, how we can use the pure condition to study non-genericity. So as I said before, this polynomial that you get is non-zero if and only if you have a generically infinitesimally rigid framework. That was how they did the proof. And the variety defined by that polynomial, so that hypersurface, is the set of frameworks associated to G that have infinitesimal motions. Okay? And so I want to spend the next few minutes studying this polynomial, this pure condition CG, and what kinds of things do I want to learn from it? I want to see if we can figure out information about rigid substructures of our graphs, of our frameworks, and to see if there are intuitive geometric descriptions of the reasons explaining these special positions. Okay? So for example, in this body bar framework, so 2 bodies, 3 bars in the plane, it's generically rigid. What are the positions? We can test, if you give me an answer, I can test it up here. When do I get a flexible one? Can anyone give me an intuitive, Danielle?
All 3 are collinear on each one.
If all 3 are collinear, so da 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 da.
Yeah, I was thinking that like they form a line on the one on the left and then form a line on the one on the right, and each of them rotating on it.
If they're all 3, if the 3 points are collinear here and the 3 points are collinear there, yeah. So I think it's not stated that way because we're thinking only about Pluker coordinates of bars. Like the joints kind of get erased in this picture, and we have to talk about bar language.
Okay.
But I think that the condition that Danielle's giving is equivalent to having the bars parallel. Okay. Is there any other situation where I get a motion? Yeah, where all 3 bars go to 1 point. And so, dun, 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 here they are. These are sort of 2 special positions where I get motion. And you could see already then that there's an advantage to thinking projectively, because instead of saying I have these 2 cases, the bars are parallel or they meet at a point, if you think projectively, you just say I have 3 bars, but the lines meet at a point. Because in the first example where they're parallel, they meet at a point at infinity. Right? And so the advantage of moving to the projective setting is that it unifies our treatment of both rotations and translations. You can think about translations as rotations about axes at infinity. And so you don't, instead of saying it's like theorems with cases, you get these sort of like much nicer theorems in the projective set. Okay, so let's see what happens. So if we're going to study these pure conditions, we need to figure out how to write them down. Okay, and so I mean, they're going to have like lots and lots of terms, and if you're someone computational, you're like, she's not really going to like get these huge symbolic determinants. It's probably a bad idea. But we're gonna write them down in a kind of compact way, noticing that our columns come k at a time. Okay. So what I'm doing here, this is the same rigidity matrix that I showed you earlier, but instead of writing out A1, A2, A3, I'm just writing the vector A. So you know that's 3 columns wide. Okay, so this is a 9 by 9 matrix, square. All right. And so I'm going to write down its pure condition using brackets. So in the proof of the combinatorial theorem, I expanded via n by n determinants. Now I'm going to go k by k. It's an n by k by n. It's a kn by kn matrix. So now I'm going to go k by k. And White and Whiteley have a nice convention for figuring out, well, which k which k by k minors go together. And it turns out that if you can orient your graph, so I'm tying down vertex 1. So I'm going to orient my graph so that all edges incident to vertex 1 point towards it. And then for the rest of the vertices, I'm going to make sure that each vertex has out degree k. So k is 3 here. So vertex 1, everything points towards vertex 1 that can. And then vertex 3, I have C, D, and F pointing out in the first version. And in vertex 2, I have A, B, and E pointing out. There's one other orientation that works. And those orientations exactly are going to tell me which minors I can take together. So the first one says I'm going to take the rows corresponding to A, B, and E, and make that bracket is the 3 by 3 determinant of the vectors A, B, E. Okay? So I get ABE minus ABE times CDF minus ABF times CDE, and that's my pure condition written as brackets. If you're someone who likes Grassmannians, you might say, hey, isn't that an element of the homogeneous coordinate ring of Grassmannian? Yes, it is. So there are other ways of writing this in terms of brackets. And actually, one of the open problems that I want to state tomorrow has to do with relating the ways of rewriting this in the homogeneous coordinate ring of the brackets and the connections to an algorithm for detecting this kind of rigidity theory, so a graphical algorithm. Okay, so we can write these things down. So what about this intuitive geometric description of why we're in a special position? So there's this thing called the Grassman-Cayley algebra. How many people have heard about it? A few people, right? So if you haven't,
I understand.
Yeah, if you haven't heard about it, I don't want to go into it here. It would take me too long. It is lovingly introduced in, I think, Sturmfield's very first book, Algorithms and Invariant Theory. And what it is, very briefly though, it's the exterior algebra. Only instead of like we're used to, where exterior products go like this, they make exterior products go like that. Because they want to think about those as, is that how we do it? Now I'm turned upside down. We do it this way. Yeah, okay, so they do it the other way. Because they want them to think, they want you to think about those exterior products as being joins, and then they have a second operation which they want you to think of as being meets, corresponding to intersection. So there are meets and joins in this algebra. And this polynomial happens to have a Grassman-Cayley factorization. So I claim in this weird algebra that has an exterior product and some other mysterious join operation, meet operation, you can write it like this. And the interpretation is that the two lines, A and B, they meet in a point. The two lines, C and D, meet in a point. The two lines, E and F, meet in a point. And those 3 points are collinear. And so this is, I claim, an intuitive geometric description. So it's saying that the bars A and B, the bars C and D, the bars E and F, each of those, you get 3 points that way. If those 3 points are collinear, this will have an infinitesimal motion. So that's an intuitive, depending on who you are, geometric description of what this vanishing of that polynomial really means. Okay, so if you're intrigued by that, you can read this paper and also Barron's book. It's really lovely stuff. All right. What does this look like in the body in CAD setting? Well, the matrix, so here this is a planar example. And so in R2, you have 3 degrees of freedom. You can think of them as, one of them is rotational. So the red rows kind of correspond to angle constraints, and you can see they have lots of extra zeros. So we have to be a little careful when we expand the matrix. It's the same example as before, but now instead of having 2 of these bracket monomials, I only have 1, because one of my bracket monomials put B and C together in the same determinant, but each of those only has 1 non-zero entry, so I can't put them together. I get 0 for that. So these, in the body CAD setting, these pure conditions factor, it's much messier, and they sort of factor unexpectedly in some ways. And just to finish up here, I want to sort of compare and contrast the body bar and body Cad worlds. In body bar, so one of the things White and Whiteley shows that each edge is in the support of one irreducible factor. And in the body Cad setting, so this is a paper with James Farr, a bunch of undergraduates that have worked on this as RE project with Audrey and me throughout the years, and Louis Theron. So we showed that each edge is in the support of one irreducible factor. In the body bar setting, each factor is the pure condition of a graph minor. Here, though, in the other setting, irreducible factors might not be pure conditions of any sort of nice subgraph or quotient graph. So it's a little more complicated here. In the body bar setting, you can see that the circuits of this matroid have the form isostatic graphs plus 1, so minimally rigid plus 1. In the body Cad setting, the circuits are completely mysterious. We tried to characterize the circuits, and like every time we thought we got them all, someone would come up with like, this is a circuit too, and we'd say, oh my goodness. So this is one of our big open questions is, can you try to characterize the body Cad circuits? Okay, but that's sort of the end of the line for pure conditions. Oh, no, it's not. It's the end of the line for body pure conditions. I want to now think about back to the bar and joint case. Okay, so the bar and joint case actually is messier, right? In body bar, they were able to get a combinatorial characterization of body bar frameworks in all dimensions, and in bar and joint, you can't do it in dimension 3. It's a little messier. So let's see what happens, and this is in dimension 2. I can also get a pure condition, and so White and Whiteley did this in 1983 in another lovely paper. People should read these papers. The algebraic geometry of stresses and frameworks. Okay, so they have their matrix, and they say we can square this one off and get a pure condition by tying down bodies. And so here, you can't just, so not by tying down, you have to tie down more than one vertex, right? Because if you pin one vertex, then the thing can still rotate around that vertex, right? The whole framework. So you've got to kind of pin 2 vertices. And so what I've done here is I've pinned down vertex 1 completely, and I've like specified sort of one of the coordinates of vertex 2. That's what I'm showing in this graph. And then, what do I do to get the pure condition? Well, again, I want to expand sort of in blocks. Here I wanted to go by 2 by 2 blocks because each of these vertices is a 2 vector. And I do this in a kind of a clever way that they do this in a kind of clever way. They notice that if you have a determinant of the form x1 minus a, x1 minus b, it really can be written as a 3 by 3 determinant. So let's put everything into P2. So instead of A1, A2, I have A1, A2, 1. I'm living in P2 now. And then I can represent that 2 by 2 determinant as a 3 bracket. So again, I'm going to have brackets. Okay? And so the pure condition of this, of that framework, well, it has 1, 2, 3, 4, 5. It's the product of 5 brackets. 2 of the brackets, the first 2, involve these extra sort of tied down, these things that I got from tying down my vertices. Okay? And White and Whiteley show those are irrelevant to the analysis of the situation. Any factors that involve your tie-down variables you can sort of ignore. And you just want to pay attention to the factors that involve the joint coordinates. So x1, x2, x3. Okay? So let's see what happens when those irreducible factors are 0. So I want to talk about factors and stresses now. Well, what is a stress anyway? So here we have my pure condition, and let's first focus on the first factor. So really, it's a 3 by 3 determinant of 3 points. So when does like a 3 by 3? What's the geometric interpretation of a 3 by 3 determinant vanishing? Those 3 points are collinear, right? So those 3 points are collinear, and then those 3 points are collinear if and only if there's a dependence on these 3 rows of the rigidity matrix. Okay? And in rigidity theory language, linear dependence on the rows of the rigidity matrix is called a stress. And there is a physical interpretation of these stresses. You can think of the rows with positive coefficients, I think, as being under either tension or compression. So the signs tell you about tension or compression. Okay. So what I see is that there's a linear dependence on these three rows, which correspond to the three edges of that triangle. So you can say that there's a stress that's imported on the graph that's induced on the vertices 1, 2, 3 that appear in the bracket. And based on the symmetries of this graph, you can see that if I took my blue bracket, I would have exactly the same slide, just with the picture on the other side, right? But let's talk about the red bracket for a minute. So the geometric interpretation of the vanishing of the red bracket is the same. It's that 3 points are collinear, right? But what changes now is what happens when I look at the induced subgraph and I look at the rigidity matrix. So the subgraph that's induced on vertices 2, 4, and 5 only has 2 edges in it. And you can see, just by inspection, that I'm never going to get a dependence relation on those 2 edges. Like, it's not, the zeros are in the wrong places. Okay? But there is a stress associated to this factor if you look at the full rigidity matrix for this framework. How can we find it? So I want to talk a little bit now about how the Cayley-Menger variety can help us find stresses in this case. So back to the Cayley-Menger variety. And this now is joint work with Svi Rosen, who's here, Louis Theron, and Cynthia Vincent. So just setting this up again, we have a graph on n vertices. We'll get a map. I'm just going to move to the complex setting. I know we really want to be in the real setting. I'm going to move there so everything works. But this is another point, though, where people, especially people interested in real algebraic geometry, can play a big role in rigidity theory. Because a lot of the theorems that people are proving using algebra, of course, only hold over the complex numbers. So I'm going to get a map phi from joint space. So I'm embedded in like CD. So I have D coordinates per joint, n joints, to C to the n choose 2, which is the space of all pairwise distances. Okay. So these are just the quadratic distance polynomials, and my Lij's are the same as David's Lij's. They're the length squares. And then I like to think of it, though, in this map that's a little triangle, where I have this thing that goes phi is for the complete graph on n vertices. But then I can project it. If I have my given graph, I can project down to the space whose coordinate span to the edges of my graph. And I can also just sort of do the composition of those 2 maps, right? So the kernel of phi is the ideal of the Cayley-Menger variety. I'm using David's notation. And here's the nice observation, though, that, and this is something that's really kind of trivial, that if you have an element, it took me a long time to understand it, though. If you have an element of the kernel of phi, so something in the ideal of the Cayley-Menger variety, it'll give rise to a stress by just using the chain rule. So f is an implicit polynomial that vanishes on this parametrized variety, right? The quadratic polynomial is parametrized a variety. So you plug all these quadratics into one of the Cayley-Menger, a polynomial in the Cayley-Menger variety, and you get 0. Now differentiate that, right? When you differentiate, you essentially get the gradient evaluated at the parameterization times d phi, which is the rigidity matrix for the full complete graph. And that's going to be 0. And so what you have then is a vector. That gradient is a vector in the left kernel of that matrix, which means it's a dependence relation on the rows of the rigidity matrix. Okay, so that gives you a stress, because that's all stress is. So how do we use this? Well, let's see. Suppose I have an isostatic, so a minimally infinitesimally rigid bar and joint framework. The triangle on the previous page was sort of the geometric picture. This is the algebraic picture. So I'll get a map of rings going the other way from the ring whose variables are the Lij's, the distance coordinates, to the ring whose variables are the joint coordinates. And suppose I had an irreducible factor of my pure condition. What do I want to do? Well, pull it back, and you get a prime ideal P. And then thinking sort of the algebraic matrix, so what I want to do now is intersect that prime ideal P with the subring generated by the variables that appear in my, corresponding to edges that appear in my graph. So this is some elimination. So this is going to be non-zero because I'm on an irreducible factor. And a polynomial in there is going to be a stress for the frameworks that are in the variety defined by that irreducible component. Okay, so this is a way of finding stresses. And so we can actually do this in some small examples. So for this example, suppose I wanted to do this for my triangle, that green triangle. We can do this, and we can see that when we do the elimination, the polynomial, we get this quadratic polynomial. I don't know how many people do a lot of distance geometry stuff, but if you're a distance geometry person, you might recognize it as the determinant of this matrix. And this is exactly the Cayley condition that a triple of real numbers has to satisfy if they're the pairwise distances between 3 collinear points. So this is exactly saying these 3 points lie on a line, which is exactly what that minor was saying. Those 3 points lie on a line. Okay. All right. So, and the exact same thing happens with the blue factor. But then there's the red factor, right? So you do this thing, you like, you take that thing, you pull it back, and then you intersect, do the elimination, and you see what happens. And I'm not going to print it out for you. It was a really big polynomial, an irreducible polynomial of degree 6, but it was supported on every single edge of the graph. Okay, and we got only one of them. So what it means is that if I have a stress on this framework that's due to the fact that edges 2, 4, and 5 are collinear, it has to be carried kind of on that union of 2 triangles up above, right? That union of 2 triangles, it's 2 rigid things put together along a facet, so it's rigid. That's acting like a single bar up there, kind of, and you need that whole thing to carry the stress. So even though each of the irreducible factors in joint space look exactly the same, it's just like 3 points, you know, these 3 3x3 minors. When you look at the corresponding things in the distance coordinates, you really see that they behave very differently in terms of the graph. Right? Some of these are supported on triangles, and some of these really are stresses that are supported on the whole thing. So it's very different. This still is just telling us about infinitesimal motions. And I want to end by talking a bit about how we can use algebraic methods to find sort of true motions. I think in rigidity theory, they call them finite motions. Like, I was confused for that when I first started. It's opposed to infinitesimal, right? So they're infinitesimal motions. Those are like attaching little vectors to your vertices. And then there are finite motions, which are like the continuous things that David was talking about. Okay, so this is the other idea we had. So suppose you have an isostatic graph, so a minimally infinitesimally rigid graph, and you say, I want to see if I can find edge lengths that Lij's, so this thing actually has a motion. Well, here's what I can do. Take some edge, E, that's not in your graph, and ask the question, are there edge lengths so that the graph G, the framework G, has a motion in which my edge E changes length? Okay? So you can add it in, and then the resulting graph contains a circuit. And here's where algebraic matroids play a role. You want to find this thing called the circuit polynomial associated to this circuit, which is just a fancy way of saying you want a polynomial whose support contains this edge E. Okay, so it's showing that you have a set of variables that are dependent, right? We did that here. And then what you can do, so you have now this polynomial. And the polynomial has to be supported on E because your graph without E was independent. Right? So one of the results in matroid theory says if you have an independent set and you add something to it and it's dependent, the dependence relation you get has to include the thing you just added. So this polynomial has e in its support. And then if you could form the ideal of all the coefficients. So look at it expanded in powers of e, make the ideal of all the coefficients. And then if you want something like intuitive geometric descriptions, look at its associated primes. Okay? So that's what we did here. This one has 6 associated primes. Some of them were not geometrically significant. Some of them corresponded to like 3 vertices on a single point, which didn't seem that interesting. The 2 that were most significant for motions were these. So what are they telling us? The first one is saying that L13 is 0. So that top edge, so really what I have is a 4 bar because that top edge between 1 and 3 is 0, has 0 length. And then it's saying, well, if you're actually going to realize that, it better be that the edge between 1, 2 and the edge between 1, 3 have the same length. And look, the algebra knows about that. Yeah? And the edge between 1, 4 and 3, 4 have to have the same length. So I'm going to squash that top edge to 0, and then I have a 4 bar. And I really, someplace I do have a 4 bar. Oh, yeah, I had models. I have a 4 bar, and here I have this one, and it really is fairly rigid. Okay. And then what is this other one saying to do? It's saying L23 is the same as L34. So L23, so that's the bottom edges of the top are the same. L12 is the same as L14, so those 2 are the same. And L45 is the same as L25. So it's saying that the way I've drawn it, which is so lovely, is those conditions make it look like the way I've drawn it. So but this is kind of a realization like that, and it's pretty rigid. So how do I have to realize this so that it has a motion? Does anyone see?
Higher dimension?
Flip it over on something.
Flip it over. So if I put vertex 2 and 4 on top of each other, I can do that, and then I have this thing that looks like a single edge between 2 and 5 and 4 and 5, and it sort of goes around in a circle. Okay, so there is a realization. Not all realizations of this have motions, but there is a realization that does. Okay,
But on the other one, they all had a motion, so that's.
Yeah, so they all had a motion, but let me see. But okay, so actually, this is the same thing that David showed us in the morning. I'm like, what? So David showed us in the morning an example of a triangle with a triangle inside it joined up. Like these 3 vertices are a triangle, and these 3 vertices are a triangle. This has exactly the same combinatorics, where you could think of the triangles as the bodies now. Okay. And in David's realization of that, it was infinitesimally flexible, but actually rigid. But it satisfied the same condition that he said, if you extend those 3 lines, they're coincident. So you can have these infinitesimal, you can be non-generic according to infinitesimal rigidity and still not move. It's sort of kind of like, I think the motions are actually sort of deeper in there, higher codimension, maybe. All right, so in summary, Barham joint rigidity theory, big open question in dimension 3. You'll be famous if you solve that. Combinatorial rigidity theory comes in many flavors for many different applications. One of the fun things about being in this group is that when I go to conferences with them, there are like architects and engineers and people in materials science and computer scientists and mathematicians, people from all over interested in rigidity theory. Polynomial methods, I think, have a lot of promise for being used to find intuitive geometric explanations for singular behavior. And many people, after David's talk, said, is there a place I could learn about this? So, Mira Sitharam, who was the fearless leader of this group, I said, people have been asking her that for years. She's one of the senior figures in rigidity theory. And she got us together and said, we should make a handbook. So this is the Handbook of Geometric Constraint Systems Principles, which is, I don't know, kind of a weird mouthful. But it means rigidity theory, what it really means. Okay, this is where you go for rigidity theory. We have chapters on combinatorial rigidity theory, on mechanisms. Frank wrote a chapter on real algebraic geometry, and one of the figures is on the front cover even.
Thanks.
Thank you for writing for us. So it's like, I think it's like 754 pages or something like that. So there's obviously a lot that I omitted and a ton I don't know, and I hope it's in that book, because, you know.
So the book's published?
The book is camera ready and to be published in days or weeks. It is coming. This is like the final version of the front cover. So it really is like
for the cover.
It's stay for the material inside.
So it really is ready. So thank you very much.
As I have a completely oddball comment, there's a relationship of this to yesterday, in that Vera, I think, is married to York Papers, who's in geometric modeling. Actually, one of the people who got us in geometric modeling and algebraic geometry.
Ah.
I think that's correct. I mean, I see them at different conferences.
I cannot confirm or deny that.
It's the same way that I'm connected to hot algebras.
Yeah.
So were these kind of like body frameworks? Are the bodies always convex?
So, okay. The way we think about these bodies, it's like you never really, in the literature, because if you're working infinitesimally, at least, the joints go away. So you just kind of, like, you just think about the Plücker coordinates of the bars and stuff like that. So you don't really think about like the shape of the body or how big the body is. Like, so in body bar frameworks, you just assume like the bodies are big enough to contain all the joints that I said were on them in a generic way. But people don't really talk about the shapes of the bodies, I think, too much. Although sometimes, like with panel hinge, I mean, they're assuming, I think, that they're like flat and they have hinges.
I feel like if it's not convex, you can also have like loops and graphs.
Yeah, I mean, I think if you're varying the constraints, then you might have to worry about your bodies. But I think we just think of them as these rigid, full-dimensional things.
I mean, I know people say this sort of off platform as movements. The first step is to forget about how the joints interfere with it, how the bars interfere with anything, and just see how it moves. And then of course they have to worry about like the cables getting tangled or tying up with the spot welder or something. But I think the mathematical question, you forget about the actual object and just think about motions.
Yeah.
It's hard not.
Yeah. I mean, right, so in particular, like, maybe your motion has, like, bars in the real world that would, like, intersect each other. You know, we try not to worry about that at first. Yeah.
On the slide where you had the red plane, blue line, and the green dot, were you, like fully, like, stopping, making it rigid?
Yeah.
Okay, so was the blue line, like, in between and stopping them from circling?
Yeah, so the blue line, I put the blue line, think of it as two lines, right? I have one line that I put on an edge of my cube, and another line that I put on an edge of the hexagonal prism, and then I said, actually those two lines have to coincide. And so now, they can move like this relative to each other along that line in space, and one of them they can twirl around the line, but I can't like.
Right. So looking at that, I was thinking they would still be able to twirl around, given that they stayed in the same. So it's,
yeah, they can still twirl. It's not. So that line coincidence eliminates 4 degrees of freedom, and the relative thing has 6 degrees of freedom. So that's why I need the point-plane coincidence and the point-point distance to eliminate the other 2.
Okay. So that is a fully rigid.
That is a fully rigid thing.
Okay.
They can rotate, but only the whole thing. They can't rotate relative to each other.
Oh, right, and that's the term. Got it.
If anybody else besides me didn't understand why it was degree 4, I finally realized it. Because the Grassman is dimension 4. So it required 2 lines to, it required 1 line to be incident on a fixed line. It's counting out 4 degrees of freedom for that second line. So that's why it's 4. And I couldn't figure it out for the longest time.
And it's been fun. Like sort of like, that kind of logic is appealing to an algebraic geometer, but like different people mean different things by geometry. My co-author Audrey St. John, when she thinks geometrically, she really thinks like, I don't know, it's a very different way of thinking, and it's been really helpful to me to see different points of view. It's been great. Thank you.
Okay, announcement time again. And actually, I need that keyboard.
Actually, before, can I have one announcement, Greg?
Sure.
So, Carlos, do you have the dates?
June 10 to 14, 2019.
Okay, so we want to announce that if you loved this conference, next summer we are going to have a big conference in Amherst right before David retires, and we invite you all to come. We hope you join us. There'll be lots of toric varieties and geometric modeling and the kind of stuff you heard here in Amherst. Yeah.
You can actually project it. No offense to the locals, but Amherst is a lot more beautiful than Fort Worth. I've lived in Amherst.
Barbecue's not as good.
Barbecue. We have Bubs. We have Bubs barbecue.
Ideas, varieties, applications.
Will it be hot enough there?
Yeah, we'll try our best. So we are calling this ideals, varieties, applications. It's a joke for the in crowd. June 10th through 14th in Amherst, Massachusetts.
Exactly, almost 8 from now.
Yeah. So join us there, please.